wanted to thank everyone for this morning. It's really fun for me to be here. Lizzie mentioned that I'm from Minneapolis. In fact, I'm sitting in Minneapolis right now, and it's cold and there's snow on the ground. So it's sort of fun to be doing something a little bit different today. So what I want to do is talk about something perhaps a little bit different that you may not have really thought about in terms of computing before. I want to talk a little bit about randomness in computing and how we can learn from the mistakes and the errors and the randomness that we have in the world. And I would like to point out that this is a picture of me standing in front of the Monte Carlo Casino in Monaco. This was taken a few years ago. And I point this out because if you didn't know, Monte Carlo Casino is where we get the name for Monte Carlo simulation. So I thought it would be useful to go to the source. Right? Well, I think every good talk should start with a story. So my story begins with Hewlett-Packard. Back in 1989, they wanted to work on something called the EPIC processor. And the EPIC processor stands for explicitly parallel instruction computing. So this was a wide word processor. And they introduced this word, the wide word processor, back in 1993. And the PA, precision architecture, wide architecture, was combined with a joint development project with Intel, where they announced this collaboration to build this next generation processor. There's a lot of hype around it, with remake the computer industry. Eventually became a multi-billion-dollar investment for Intel and HP. Several students of mine had gone to work for this joint venture at the time, so I was kind of familiar with what was happening there. Well, in 1999, October, Intel announced the name Itanium. So many of you have probably heard of the name Itanium. This was their instruction level parallelism processor, 64-bit native dative types that would be best in class. It would be used in all servers all over the world all the time, things like that. So it was really quite exciting. In summer of 2001, they released the first Itanium. So you could actually buy one and do some performance evaluation on it if you were so inclined. Then in December 2001, there's what I consider a rather extraordinary paper that came out at the International Conference on Microarchitecture. You might know that as MICRO. And the paper was published by Intel, written by Intel. Actually, one of my former students was the primary author on the paper. He was working at Intel at the time. And the conclusion from the paper was, this Itanium doesn't work quite as well as we expected. So what was happening here? Well, they tried a really neat idea. It's called instruction predication. The idea is on the left here, you've got a sequence of instructions with some branches in there. And we're going to change the sequence of instructions and get rid of all those branches. And instead of having those branches, we're going to put in what are called predicates. So P1 and P2 are predicates that correspond to these sequences of instructions. And the predicates get computed, and then the instructions get run through the pipeline. And if the predicate is true, the instruction gets committed. If the predicate is false, the instruction gets nullified. So you eliminate all branch instructions. It improves the pipeline performance, increases parallelism opportunities, and basically makes everything work much more smoothly. At least that's the idea. Well, the reality turned out to be just a little bit different than what people were thinking. The reality was that in 1994, or the potential rather, was in 1994, there were a paper published by Scott Mulkey that said, we think this branch predication idea can get somewhere around 25, 27 to 56% fewer branches and branch mispredicts. In 1995, yet another paper said roughly the same thing. If you do full predication, you can get this pretty substantial speed up. In 1998, one of his colleagues, David August, published another paper, and this said that you can get 30% speed up if you just do predication all by itself. In Itanium, they actually built this idea into the processor, wanted to give it a try, and found out that actually you end up with about 7% fewer branches, maybe 24% fewer branch mispredicts compared to the potential, which said, maybe like 27 to 56%. And the speed up that was predicted for predication was in the high double digits, when in fact they got 2% average speed up. So the question, of course, is what happened? Why was the difference in performance? We had these great expectations and ended up with 2% average speed up. Well, one of the big differences was that they originally designed the Itanium, or designed the branch predication idea, I should say, using the spec int 95 benchmarks. Those benchmarks are dominated by branch instructions. When they actually built the processor and released it, 1000 was available, and that benchmark was dominated primarily by memory accesses. So they tested it with a different benchmark than they designed it with. Also, the hardware capabilities for the simulations, typically they were looking at 8 issue with full 8 ALUs versus in the real Itanium, they had 6 issue with only 4 ALUs. So you had more competition for resources in the real hardware. The compiler capabilities were different. The simulations presumed that you could do predication everywhere. In the Itanium, they actually had to use a real compiler, and found out that it didn't always work quite as well as it could have, or as well as the optimistic assumptions assumed that it could. And also the real hardware had some real overheads. So the operating system existed in the Itanium. It did not exist in the simulations. That real hardware delays versus simulated assumptions, full input sets versus small input sets for the simulations, and so forth. So it's basically designing with old benchmarks and facing the realities of real processors. So the question I ask from a performance point of view is, what can we learn from this? Well, one thing we learn is that designing a processor today, you end up using yesterday's benchmark programs, but you're going to evaluate it with tomorrow's benchmarks. This is a hard thing to do. We call this general problem benchmark drift. Benchmarks change over time. And real measurements versus simulations don't always give the same results. Simulations, you make a lot of optimistic assumptions, or you fill in the blank on things that you don't really know are going to happen. But when you get to reality, you have to deal with these real overheads. And assumptions and capabilities change over time. What made sense today when I designed the processor doesn't make sense 5 years from now when I release the processor, because capabilities change, technology changes. I can do things today that I couldn't yesterday, and that will change the capabilities of what I'm able to design into a processor. And it's tempting to overinterpret simulation results. As performance evaluation people, computer architects, we sometimes get a little hung up in thinking our simulations are really telling us the truth, when in fact, no, there's a lot more to it than that. Well, the lesson that I take home from this is that we really need to teach performance evaluation as a fundamental skill in our computer science, electrical engineering, computer engineering curricula. It's too easy to not understand what's really going on. And I think this quote from Grace Hopper really sums it up. One accurate measurement is worth 1,000 expert opinions. Doesn't matter what you think. What can I actually measure? What do I actually see in that real hardware? And this really helped prod my interest in performance evaluation and really pushed me further down that path to think about, okay, what really happens in this random world? What really happens when errors occur? You know, we think about errors as causing a fatal program failure, for instance, or we think about errors as being some probability distribution. We try to explain those errors in some sort of statistical way, which I'm trying to hint at the left there, where we look at confidence intervals to explain how big errors can be. But sometimes errors can lead to really interesting insights, things that we hadn't really thought of before. So as I was digging deeper and deeper into this sort of statistical world, simultaneously some colleagues of mine were looking at new technologies. and what can we do with these new technologies? And things they were looking at were things like deep submicron CMOS, looking at spintronics, carbon nanotubes. All of these sort of new technologies give us very high densities. You get more bits, you get more transistors, you get more logic, you get denser interconnects. So you can do more with these sorts of devices. And the question is, how do you take advantage of that, and what problems come up with that? In fact, what you find with these new technologies is that they're very, very sensitive to noise. Little variations in the structure can make big changes in the operation of the device. The structures are so small that alpha particles and outside sorts of interference can change bits. There's large variations when you manufacture this. So I designed a transistor to have this particular characteristic. And as it turns out, when I build it, it doesn't really have that characteristic. Things change. And we can describe these defect rates, these variations statistically, but we have to somehow deal with these high error rates. Well, we as performance analysts, we learn a lot about statistics. So the work I was doing, looking at statistical performance modeling, talking with my colleagues about this, we got together and said, is there something we can do together here that can look at these noise characteristics on these devices and then somehow take advantage of that, or somehow maybe describe that, or what can we do with that? So this led me in kind of an unexpected new direction in my research. The conventional assumption that people have in computer systems is that noise is bad. So I have some noise come into the system. I have this alpha particle come in and hit a memory location, for instance. And what was a 0 becomes a 1. What was a 1 becomes a 0. We get these bit flips, which causes the wrong output. So we were trying to compute X, and we ended up with X plus Z. This is bad. At least that's the conventional assumption, that this is bad. So our question was to say, can we somehow use this random noise to compute reliably? Can we somehow take advantage of this in order to actually make these systems more reliable? So what do? Well, we look at it from the point of view of computing approximately. So we're going to say that I don't have to have a perfect answer. And there are many problems in the world for which I don't need a perfect answer. And we're going to think about this as computing on probabilities. So we've got a digital circuit here in the middle, and we've got probabilities coming in, and we want to compute something and produce this probabilistic output. So think about values between 0 and 1. I do some sort of mathematical operation on those, and I produce this value that's an output between 0 and 1. And if you want to think about controlling the system, for instance, with these, I can think about scaling this if I need to. I can amplify it, whatever. Let's just, for this point, think about probabilities. One of the key things, however, is that this digital circuit is just conventional logic. We have AND gates, OR gates, XOR gates, multiplexers, and so forth. So we're just going to use conventional logic, but treat the inputs and outputs as if they're probabilities. Now, what can we do with this? Well, let me give you a quick example to sort of motivate this idea. So here's two images, and I'm going to do what's called an image difference. So logically, I'm doing a subtraction between the two images. It's a little bit more complicated than that. But by doing this logical image difference, I get something like this figure on the right. And this shows me that there's been a change from the first image to the second image. So this is useful for detecting movement, for instance. I can see that, okay, I've got a camera monitoring this area. If something moves, then I see this sort of this shadow image move, and I can tell that something changed. All right, so one of the advantages of this stochastic computing, this probabilistic computing, I'll demonstrate here. So if I look at a conventional computing approach, and I'm doing this image differencing problem, if I start to inject errors, so on the bottom I show error rates that are injected into each one of those images. And you can see as I inject more and more errors, the picture becomes fuzzier and fuzzier. I get more noise in the image. At some point, the noise washes out the image and I can't see what it is. Conventionally, I could do something like TMR, triple modular redundancy, and to do 3 copies of the circuit, and then I vote and take the 2 that match and call that the output. And I see that I get better image quality for longer, but up here when I get high error rates, I still see bad things happening. I still get a lot of noise in that image, a lot of salt and pepper. The stochastic computing approach, however, on this last line, you can see that, excuse me, you can see that I can inject a huge number of errors and the output basically doesn't change. It looks the same with 0% error rate as it does with 30% error rate. So there's something here with this stochastic approach, this probabilistic approach, where I can have a lot of errors, I can tolerate a lot of errors, and I can see that, this image doesn't really change this much. But how do I do this? Oh, another quick example. First, demonstrate a slightly different point here. This is another image with gamma correction, we call it, and 1%, 2%, 10%, that's the error rate in these images. If I do this stochastically, what you see is I increase the errors in this black and white image. For this particular gamma correction function, the output just sort of fades to gray as I get more errors. So I get this very graceful degradation as errors are introduced into the images. They're introduced into the overall circuits. All right, you may be familiar with probabilistic analysis. So probabilistic analysis, when we think about probabilistic inputs that somebody generates, and this circuit is known, somebody designed this, we know what it is, and then we want to capture the outputs. You may have seen this for testing of digital chips where I generate random inputs and I look at the outputs, and if I know that particular chip is good, I know what the signature should be, so I can do this random testing on the chip. That's not quite what we're doing here. We're starting with probabilistic inputs that somewhere are being generated. These are the inputs to our system. And we're defining what we want the outputs to be. We've got some transfer function within that circuit. We say if the inputs are this, we want to transfer them to the output like this. So just think of it as a functional transformation. Our job then, excuse me, is to design this digital circuit in order to do that transformation. All right, so how do we do this? Well, think about these inputs as truly probability values. So I have these values coming in on the left, 4/8, 3/8, 4/8, 7/8, whatever. And I do some function within this combinational logic circuit to generate my desired outputs. In this case, I have 2 outputs, one that's 5/8 and 3/8 when the inputs are that value. Now, how do I come up with these probabilistic inputs? Well, we're going to think of this in terms of serial bit streams, where I have a series of 0s and 1s coming in, and the fraction, the fraction of those 1s out of the total number of bits, that's the value I'm representing. So for instance, on the left, in the upper left corner, I have 0, 1, 1, 0, blah, blah, blah. I have 4 1 bits out of a total of 8 bits. So I'm representing 4/8 or half. If I go down to the lower left, I've got 7 1 bits out of 8 bits, so I'm representing 7/8. Now, if you think about running these bit streams longer and longer and longer, then I can go to hundreds of bits, thousands of bits, and I can get the resolution that I want for that particular value just by running the bit streams for longer, right? But the key thing now is to just think that I'm generating a probability value or representing a probability value by the number of 1 bits out of the total number of bits for a given time, t. All right. Why would we want to do this? Well, here's one key benefit of this. I get very cheap, very inexpensive arithmetic operations. For instance, if I take these 2 bit streams on the left and I AND them together, I get the bit stream on the right. And this ANDing operation does a multiplication of the 2 probabilities on the left. So the equation below this shows that the output C, the probability of getting a 1 anywhere in that output stream, is equal to the probability of seeing a 1 on A times the probability of seeing a 1 on B. So if I think of this as A, B, and C being these values between 0 and 1, then I'm just taking A and B and multiplying it together to get C. Cool. AND gate gives me very inexpensive arithmetic, very inexpensive multiplication. I also get very inexpensive arithmetic for doing addition. Now it's a little bit different here. I get this scaled addition. So I have A and B coming into this multiplexer, and I have T is just a serial bit stream that's switching between the two inputs A and B and putting the value on the output C. What this really does is the equation in the lower left corner is taking the value T, multiplying it by A, and adding that to 1 minus T times the value of B. So by choosing T, whatever value I want between 0 and 1, I can get this weighted value of A and B, this weighted addition of A and B. Turns out to be an extremely useful operation. Another key benefit is that I get this fault tolerance. As I demonstrated on those images, I can get this sort of graceful degradation as I get more errors introduced. If you think about what happens in a conventional circuit, I've got these two values that are being multiplied together. If one of those bits gets changed from a 0 to a 1, that value goes from 2/8 to 6/8 because I changed the most significant bit. I get a big change in the output value. If I'm doing a multiplication stochastically, I can change any one of those bits and I just get a single bit resolution error. So if I have 8 bits in this case, I get a 1/8 bit or 1/8 error on the output. If I extend this out to 200 bits, 1,000 bits, then I get 1/1000th of an error for any bit that I flip. The other interesting thing about this is that these bits can change independently, and it's as likely as a bit to go from 0 to 1 as it is to 1 to 0. So if I have multiple bits changing at the same time, then they tend to cancel each other out. So I get perhaps lots of errors coming in, but these bits get randomly flipped, so they cancel each other out, and I don't see as much error coming out the other side. All right. How do I now synthesize this logic to take advantage of some of those things that I just talked about? Well, here's kind of a high-level view of the problem. I've got an input T coming into this combinational circuit, and I want to generate this function G of T. And I want to somehow come up with a way of synthesizing the logic to implement that particular function. So let's back up a minute, take you back to your old signals class, where we talked about Fourier series. And if you remember Fourier series, this is the idea that I take multiples of a wave and I add different combinations of those waves, and I can produce any output that I want, any wave shape that I want, simply by selecting different combinations, different amounts of each one of those periodic signals. So in this case, by appropriately selecting these periodic signals, I generate this nice square wave. I can make that square wave look as good as I want by extending that out to as many terms as I want. We use what's called the Fourier basis function for this. So Fourier basis function is this periodic function that I showed here, this b sub n. And then I just make a linear combination of these basis functions using these Fourier coefficients c of n, and I get my function f of x output. So by choosing c of n, given this basis function, I can generate any wave shape I want. So keep that idea in mind. And what I'm going to do next is simply choose a different basis function. This Fourier basis function, that's just one possibility. I'm going to choose a basis function that's called a Bernstein basis function. And this looks kind of strange. You probably have never seen this before, or at least not in this form, but it is simply another basis function. So I can do the same thing. I can form a linear combination of these Bernstein basis functions by choosing these Bernstein coefficients. And by choosing these coefficients correctly, I can generate any function I want to match whatever function I desire to synthesize in that circuit. Why the Bernstein basis function? We'll get to that in just a second. How do I come up with these Bernstein coefficients? Well, I'm going to start with this Taylor series expansion of the function g of t that I want to compute. So if you remember Taylor series expansion, I'm just choosing various powers of t with these coefficients, a of n, to define that function. And in this case, I'm going to equate it to this Bernstein function, this Bernstein polynomial. And all I need to do is solve for those Bernstein coefficients. It looks a little messy down at the bottom, but it's easily automated. I can do this in Mathematica or something like that and easily find those coefficients, given that I know what the Taylor series expansion is of this function I'm trying to implement. Sounds like a lot of steps, but it's actually pretty straightforward. Why the Bernstein basis function? Well, if you look at what happens in this multiplexer, that Bernstein basis function looks a lot like that operation that I get out of that multiplexer. So by choosing these coefficients carefully for this Bernstein polynomial, I come up with a structure that we call probabilistic multiplexing. So I have a big multiplexer here that's essentially implementing the Bernstein polynomial. And then when I operate this, I have these Bernstein coefficients coming into the left-hand side of the multiplexer. I have copies of the input coming into the upper left corner. I add those inputs together, and I produce this selector point, this selector input for the multiplexer that I randomly cycle through these different coefficients. If I do that appropriately, then I get the value coming out on y, that is the probability of y being a 1 at any particular point in time is equal to that Bernstein polynomial. The nice thing about this is that I can change coefficients and I get a new function. So it turns out to be a very reconfigurable sort of system. So let me give an example of how this works. So here's a function that I want to implement. This f of t equals 1/4, blah, blah, blah. I equate that to the Bernstein polynomial. I find the Bernstein coefficients, and I get this equation using the Bernstein basis function that's exactly the same as that function that I'm trying to implement. So I take these coefficients, 2/8, 5/8, 3/8, 6/8, and I feed those in the lower left-hand corner to my multiplexer. And I've got some random number generator that's generating all these coefficients. And I have another random number generator that's generating the input value, in this case, 4/8 in the upper left. So I have the coefficients coming in at the left. I have the input in the upper left. And the output is that function f of t that I call y, excuse me, in the lower right-hand corner. So how this works. At that upper left, I look at all the bits of the inputs that are coming in. I add those together and I get the value 1 in this case. That says I'm selecting input 1 for the multiplexer, so that value 0 for that coefficient goes to the output y. So I've generated 1 bit for that function. I repeat that process. So I do it again for the next input bits on the inputs in the upper left. I sum those, I get the value 2, select the second input to the multiplexer, and that gives me another bit to the output, and then I just keep clocking through that, and I keep generating values for this function. Right? It looks a little weird, but it actually works extremely well. The distribution of ones at the output of the multiplexer will be exactly the distribution of ones I would get when I compute that Bernstein polynomial. Now, this is just using combinational logic, and I'm limited to the functions I can get out of this. I'm limited to functions that are just basically Taylor series expansions of functions. But there are some things like periodic functions or trigonometric functions or exponential functions that are a little bit more difficult to generate. So I have to use some additional logic to do some sort of finite state machine. But the basic idea is the same. I've just got registers and logic gates on the left, which generate my finite state machine. I choose the values of A, I choose the values of K in order to make this target function match what the function is that I'm trying to generate using some sort of least squares minimization process to choose those coefficients. And if I do that, I get an output that in fact matches that target function that I'm trying to generate. And I can use this to generate transcendental functions, periodic functions, thresholding functions, things like that. I can go into a lot more detail on that, but that's for a different talk. Here, a question is, how do I measure performance of these sorts of things? How do I compare these to other sorts of devices? Well, we're going to look at area delay product because we're just looking at circuits at this point. We're not looking at complex systems like a full computer system. That's a little bit further down the road. I'm going to look at the area delay product. So I'm going to take the area of the circuit for a conventional deterministic system, take the area in terms of number of gates. I'm going to multiply that by the number of cycles that it takes to generate a result, and multiply that by the delay, the critical path delay through that circuit. And I get this area delay product, which I call the figure of merit. If I do that for stochastic, I do the same thing. I take the area of the circuit, multiply it by T of S in this case, which is the delay to get through that circuit. But now the latency to get through that circuit is 2 to the M. So think about M. Think about M as being the resolution I want for this circuit. So if the circuit on the left has M bits, then I need to generate 2 to the M serial bits in order to match the resolution on the circuit on the left. Turns out it's not quite that bad because if M is large, then those additional bits don't really have much impact on the final result. So I can truncate some of that. But for now, just think of it in terms of this long latency to get through the stochastic system. The advantage the stochastic system gets is in area. As I mentioned, this is very cheap to implement. I have AND gates doing multiplications, multiplexers doing additions. Since I have very small circuits, the critical path delays are very small, but where I lose is in the latency. Conventional circuit has much better latency than this probabilistic, the stochastic circuit. As a quick example to compare these, let's look at a quartic operation for implementing trigonometric functions. I don't know if you're familiar with quartic operations, but quartic approach uses only shift and adds to generate these trigonometric functions, sine, cosine, sinh, cosh, and so forth. So it's very cheap compared to doing this in a conventional way. And then the stochastic implementation, I only show one stochastic version for all these different functions because all I need to do is to change the coefficients to get all those different functions. So the circuitry doesn't change for the stochastic function. And this shows the area delay product for these quartic trigonometric functions and the stochastic function. If I have 8 bits, so I have 2 to the 8th resolution of precision on this, then I've got the stochastic implementation wins in the area delay product. If I go to 9 bits, the stochastic implementation still wins. If I go to 10 bits, now the stochastic implementation wins for a couple of cases, but it loses for a couple of cases. And this is because in stochastic implementation, I have very high delays when I get a large number of bits. Even though the cost is really low, that delay kills the area delay product. All right, so that's just some simple approaches or some simple circuits there. Let's look at some image processing examples to just see, how general is this idea? Well, I can do some edge detection, median filter noise reduction, contrast enhancement, and kernel density estimation. And that's where I'm doing that image differencing. So if I look at these, the circuit, take one of those little blocks, and that's implementing this arithmetic operation at the bottom. And I'm doing that for each pixel. So I take that little circuit and I replicate it for however many pixels I have. And I end up doing all these pixels in parallel. So I generate from the input on the left, that image on the right, and I do that in 2 to the M clocks, where M is the number of bits that I want to represent in this. So I'm doing 4 bits, 2 to the 4th clocks, 8 bits, 2 to the 8th clocks, and so forth. Median filter noise reduction, I'm just really doing a min-max comparison. So I end up with a circuit like this. That tan H function in the middle is really just doing a thresholding comparison, which one is bigger. And again, I replicate that circuit for each pixel in the image. Contrast enhancement, I'm implementing this little equation at the bottom here, and I essentially doing a gain function on the input to the left to generate the output on the right. This is a little bit more complex circuit. Each one of those, that circuit that I show there gets replicated for each pixel, and it's implementing this function in the lower left corner. So I have this exponentiation. This requires a little bit more complex circuitry using this finite state machine, but it's still relatively inexpensive. Certainly much cheaper than if you were doing a conventional implementation where I had to do this exponentiation, this absolute value, and this sum. So while it looks a little bit more complex, it's still very inexpensive compared to the conventional approach. All right, so what's the cost performance trade-off with this? Well, if I just look at the normalized hardware cost, so this is looking at the two-input NAND gate equivalents to generate these circuits. And I normalize that to the cost of the stochastic implementation. So the stochastic implementation is 1 of blue bars. And the edge detection, you can see that's about 7 times more expensive than the stochastic implementation. That's the deterministic implementation, the conventional approach. The median filter, it's about 6 times more hardware. The contrast enhancement is about 16, 17 times more hardware. And for that image segmentation, it's about 267 times more hardware in terms of NAND gate equivalents. So the cost for doing that image segmentation stochastically comes down by a factor of 267. If I look at the normalized area delay product, however, I see that the image edge detection, median filter, contrast enhancement, those are much, much less expensive in terms of area delay product than the stochastic implementation. The kernel density estimation, this image differencing, that still wins by a factor of 4.5 for the area delay product. The problem here is that I have this 2 to the m bit delay, this 2 to the m bit latency to compute those results for the simpler circuits. While the more complex circuit, I still have that 2 to the m delay. However, the circuitry is so much cheaper that it trades off with the area delay product, and I still win. The question, though, is how can I reduce that latency? How can I get rid of that very expensive 2 to the m delay? What we looked at is time-based encoding. So instead of having one pulse represent 0, another pulse represent a 1, and so forth, instead we're going to use the duty cycle of a single pulse to represent the value. So if I want to represent the value 0.5, I have the pulse high half the time, low half the time. Then I can repeat those pulses to get finer and finer resolutions or finer and finer precisions out of the computation. But in one cycle, I can represent the value. If I represent the value 0.25, then I have a 25% duty cycle. The interesting thing about this is I still get this very inexpensive multiplication and the very inexpensive adding. So multiplication is an example here. If I take these 2 waves coming in from the left, these 2 pulse streams, on the left, upper left, I've got a pulse stream that's encoding the value 0.5. And the stream below is encoding the value of about 0.75. And I multiply those together through this AND gate, and I get this funny looking bit stream on the right. Well, the thing about this is that I don't really care what that bit stream looks like on the right. All I have to do is integrate that for some period of time. And I'm looking at the fraction of time that that output is high. That's my final value. So if I want a very quick approximation of the output, then I just integrate that for a short period of time. If I want a better approximation of the output, then I integrate that for a longer period of time. So this provides me a way of getting rid of that 2 to the m latency and replacing it with integrating over 3, 4, maybe 10 cycles in order to get a pretty good approximation of the output value. How well does this work? Well, one quick example here, looking at the median filter. the circuit on the left now becomes 2 XOR gates and a multiplexer on the right when I do this time-based encoding. And if you look at the table, you can see that the area for that time-based encoding drops about 63% compared to the area for a standard binary implementation. The delay goes up by about 30%, but the area delay product goes down an average of about 53%. And interestingly, the energy goes down by about 13% as well. So this time-based encoding is a way to take advantage of both that stochastic implementation of the bit streams, all the advantages I get from that, and reduce the cost by getting rid of that 2 to the m latency. Right. So this sort of computing, you're not going to use this every day. You're not going to use this for computing your bank balance. I don't believe. I want to know down to the penny what my bank balance is, but I might use this for some sort of image processing. I'm going to use it for an approach where the answer that's close enough is good enough. So I want to do some sort of approximation. I want to look at an image, and that image doesn't have to be perfect. It just has to be good enough. And as I say, I got into this starting from my experience in the performance evaluation world. I had a lot of experience doing the statistical analysis. Turned out to be a perfect fit for doing this sort of stochastic implementation. The key idea is that we use this randomness to tolerate noise instead of just describing it. We can use it to live with it. We get this graceful degradation to errors. As errors get introduced into the system, the image sort of fades to gray. It works extremely well, even in very high error environments. It's low cost. I could do multiplication, which in binary would be a pretty expensive operation. I can do that with a simple AND gate. And it's high performance when we have this time-based encoding. There's some interesting issues that you have to think about in an analog sense when you do this time-based encoding, but we're sort of combining an analog approach with a digital approach and getting the benefits of both. And there's some fun math involved. For all of us nerds who like to do this performance evaluation, probabilistic computing sort of thing, yeah, it's fun. The lesson I take from this, in a broader picture, however, is that randomness happens. There's a lot of randomness in the world that generates errors, a lot of things that we just can't control. So instead, we want to take these opportunities as they come along. And one opportunity in that stochastic computing is using the errors in order to tolerate other errors. But also from a career perspective, if you stand back, you think about, I never would have gotten into this sort of stochastic computing stuff had I not been doing a lot of this performance evaluation. I would never have seen one dot connecting to the other. This quote from Steve Jobs gets to that point. He says, you can't connect the dots looking forward. You can only connect them looking backward. So you have to trust that the dots will somehow connect in your future. And I think this is a classic example of that. I had no idea where this was going to go, but I was interested to see, how does this dot connect to the next dot? Looking back, it makes perfect sense. Looking forward, I never would have guessed. Let me wrap up here with just a couple of thoughts about communities. And when I'm talking about communities, I'm talking about research communities, but also broader communities that you live in. I've had the opportunity to live in at least 3 different architecture or computing communities: the computer architecture community, parallel computing community, storage systems community. And the common theme with all of these is that they're all based off this performance evaluation. I find the performance evaluation community to be one of the most friendly, cooperative, and inclusive communities of all that I've dealt with. And I think that's because this community draws from a very broad range of other communities. And I think community matters. I think that's the lesson I take home from this, is the community that you end up in affects your choices, your options, and ultimately the decisions you make. I was in a community that people were looking at these advanced technologies that then sent me off in a certain direction. I think you want to surround yourself with people who are smarter than you. You want people with similar interests so you can talk to them, but also people with different interests so you get different perspectives, different ideas. Try to learn from everyone along the way. You'll end up with these unexpected connections that will allow you to apply your skills in new areas and new ways. And there's some interesting opportunities that will come out of that. Just a few thoughts to wrap up here. Errors happen. We see that. We saw that in the Itanium and the interpretation of those simulation results. Measurements are much more important than opinions. You have a data point that's much more valuable than just your opinion. The community you're in matters, and make yourself available to unexpected connections. Ultimately, randomness can't be ignored, but it can be useful. You may use it when you're out gambling, hopefully not too much of that, but it also can be very useful in computing. So let me leave you with this final thought. Enrico Fermi said there are two possible outcomes. If the results confirm the hypothesis, then you've made a measurement. If the results are contrary to the hypothesis, then you've made a discovery. And I expect that we want to see many more discoveries in the future. Thank you. I appreciate your attention.